I chose to do the video solution for problem 2. Problem 2 states the figure shows a small particle of mass m equals 3.1 times 10 to the negative 12 kilograms and charge q equals negative 6.0 times 10 to the negative 6 coulombs. The particle has an initial velocity of 8.4 times 10 to the third meters per second as it enters a region of uniform magnetic field. This particle is observed to travel in the semicircular path shown with radius r equals 4 centimeters. Calculate the magnitude and the direction of the magnetic field in the region. So for this problem, in order for us to be able to fully understand what we need to do, we would have to go back to section 29.7, which is the magnetic force on a moving charge, which is the exact thing that we have here. When you read chapter 29.7, if you look at the definition of cyclotron motion, it's the situation we have here, which is a particle moving perpendicular to a uniform magnetic field undergoes uniform circular motion at constant speed. This is called cyclotron motion of a charged particle in a magnetic field, and this is what we have here. So I listed out the knowns. The first known is the mass, which the problem states is 3.1 times 10 to the negative 12 kilograms. The next known is the charge of the particle, which is negative 6.0 times 10 to the negative 6. The initial velocity is given to us at 8.4 times 10 to the third meters per second, or 8,400 meters per second. And the radius is 4 centimeters, which translates to 0.04 meters. Some of the equations and concepts that we'll be using today is equation 29.18, which shows that the force on Q is equal to QV times B. And then the next equation that we're going to use is 29.19, which states that F is equal to QVB, which is also equal to MV squared R. And this is what we'll be using to actually solve this problem. And then another thing that was important in chapter 29.7 is figure 29.7, which actually depicts a positively charged particle, and it shows that in a uniform magnetic field, it moves in a counterclockwise direction. From that, using the right-hand rule, we can determine the direction of the magnetic field for that is out of the plane. And this becomes relevant later when we're trying to determine the direction of the magnetic field. So for the actual math of this, as I said, I used equation 29.19 in chapter 29.7, and I went ahead and isolated B, as you can see here. Isolated B, as it says here, and once I did that, I found that B is equal to MV over QR. So since we have all these values, which is a simple plug and chug, again, I plugged in the mass, I plugged in the initial velocity, I plugged in the radius, and I plugged in the charge. When I did that, I got negative 0.1085 Tesla for B. And for the explanation of the direction of the magnetic field, I said, as was specified above, figure 29.7 depicts a positively charged particle, and it shows that in a uniform magnetic field, it moves in a counterclockwise direction. From that, one can use the right-hand rule to determine the direction of the magnetic field to be out of the plane. On the contrary, this is a negatively charged particle moving in a clockwise direction, and therefore using the right-hand rule tells us that the direction of the magnetic field is into the plane.